This video is for review quiz 4.1 and 4.2. We're going to be dealing with exponential and logarithmic functions. The first problem here is talking about transformations of e to the x. Now e to the x, a basic function, looks like this. On the graph, we only are up here on the top. Right here is going to be 1. And it asymptotes to the x-axis. It gets closer and closer and closer and closer and closer, but never hits it, going closer to 0 as x gets larger and larger in the negative direction. So we're trying to figure out what does the regular function look like. It's going to look something like this, and we're going to graph that here. And what does this transformed function look like? If you remember from a different video, our transformations look like this. Y equal to a times f of bx minus c plus d. A and b are multipliers, so they stretch or shrink a graph. C and d are adders, or adding or subtracting. They're adders, and they shift the function. The question is, how do they shift it? Well, as you can see here, if c is positive, it's going to be shifting towards the positive x direction. So positive c goes to the positive x, and negative c goes to the negative x. But of course, on the inside of the function, we have bx minus c. So it's going to be the inverse of what you think it is. So for this function here, we have bx minus c. There is no b and no a. There's no multipliers here, so we don't have to worry about that. But there is a c and there is a d. On the inside of the function, meaning on the innermost part of it, in other words, e to the inside of the function, x plus 1 is on the inside. We have x plus 1. The only way for that to be true is if c is negative 1. So c must be negative 1. In other words, it's being shifted 1 unit in the negative x direction, or 1 unit to the left. We're going to shift it 1 unit to the left, and then d works how you'd think. Positive d goes to the positive y direction, positive d goes to the positive y, negative d goes to the negative y. And this one is the exact same because we're adding here. So if we have plus 3 like we have here, we're going to be going up 3 units. So that one works the same. It's the way that you think it should work. It's the innermost one that works kind of opposite of how you think it should work. We're going to shift f of x upward by 3 units. All right, so let's graph this thing. This is pretty much just saying graph it. We don't have to do a vertical stretch or shrink at all. I'm wondering if they are asking for use transformations of the graph to graph the given function. Be sure to graph the equation of the asymptote as well. And then we can go from there. So we are going to shift this function. We're going to vertical translate it up by 3 units and horizontal translate it by -1 unit. These are exactly what you'd think. 3 units up and 1 unit to the left, or -1 unit. Our base is e because it was given to us that e to the x minus 1, so that's fine. And we're not stretching or shrinking at all. There's no reflection either. There's no negative multiplier. So that is good for that one. And then we're going to graph the asymptote. So this is our new function. You can see that the original one, right, it would be at 1. It got shifted up 3 units and left 1 unit. So that's where the originally should be, right here, on the y-axis. So this point is right here. Up 3, left 1, and the inner asymptote is right here. That got shifted up 3 units. You could say it got shifted left 1 unit, but it doesn't really matter because it's a flat line. It also needs to be dotted, so make sure it's a dashed line because that's not a function. It's just the function gets close to. And that's what you're kind of expecting there. The equation of the asymptote, that is just the equation of this flat line, which is y equal to 3. Y equals 3. That's the equation of this dotted line here. Okay, what is the graph of the domain? The domain for this entire thing is, you can see it definitely goes on and up off towards negative infinity. And this one shoots upward, but it does eventually hit all of these x values, all the way up to positive infinity. It's very, very slow to get to very high numbers of x, but because it shoots up so fast, but it will eventually get there. You can plug any of the numbers of, from the positive x direction into the function and it will work. So our domain is going to be negative infinity to positive infinity. Right? And the range on this function, you can see the lowest value is at 3, but not including it. It asymptotes to 3, meaning it gets closer and closer and closer to it, but never touching it. And it goes on up towards positive infinity. That should be pretty obvious. All right, let's check it. And everything is correct there. So make sure you're graphing both the function and the dotted line for the asymptote. Okay, similar thing here, but instead of a positive, like a number greater than 1 as the base, which looks like, the graph I just showed you, here we have a number that's less than 1, so it's 1/3, so it's a decimal, a fraction of 1. And what that does is that actually changes the look of the graph to being like this to look like this. It actually does a horizontal flip. And so the process though is the same. I can show you the graph of it. I'll show you the base of that one. It says this right here is the graph that I was showing you. And we're going to transform this function in some way. So how do we transform it? Well, the same idea we're looking at for all of these parts, A, B, C, and D. There's no multipliers here. There's nothing multiplying the function or on the inside of the function. So there's no A and B. There is a C and D. We have x minus 4. The only way to get x minus 4 here is if C is a positive 4. So x minus a positive 4 gives you x minus 4, which means we're going to be going in the positive direction. So we're going to be shifting to the right 4 units. And the plus 2 is a shift upward of 2 units. Okay, let's graph this thing. The base is already correct. We're going to be shifting upward of 2 units. And a horizontal translation of right 4 units. So that should be 2 units and 4 units. And we're going to graph the asymptote. This line right here. You can see it flat lines down to this point right here. And so I just created a flat line right at that point. It won't go any further down. If you're at all confused of that, let me delete this thing. The asymptote is going to be for this line right here. It's not going to go down any further. It asymptotes very, very quickly to whatever the asymptote's at. And in the normal case, it's 0. It goes there very, very quickly. So you'll see it right there that's the asymptote line. So y equal to 2 is going to be our asymptote, and I'm going to be dotted line there. As I said, it's going to be y equal to 2. Or for the original function, it's going to be y equal to 0. That's always the case for a normal exponential function. And then for the shifted function, it's going to be y equal to 2. It's always going to kind of be whatever this vertical translation. So if it's going to be positive 2, it's going to be y equal to 2. If this was like -5, it'd be y equal to -5. Let's check it. Okay, let me see what I did wrong here. Oh, I just missed that it wants us to graph both the function and the shifted function. So I just need to add in the original function as well. I'm not doing any translation to it. I'm just leaving it the way it is. So that's the original function there. And the asymptote for this one is just the x-axis. Dotted line, save that. So this is our original function. and it got shifted. We can find this anchor point right here at the y-intercept of 1. Going 1, 2, 3, 4 units over, 1, 2 units up. That's the shifted. And you can see the asymptotes and everything there. And now that's completely correct. Okay, let's move on to the next one, compound interest formula. This is a classic application of exponential functions. It's a fantastic use for it. And this first formula deals with interest that is not continuously compounding. That's what you normally would have for like a bank or something like that. And this second function is a continuously compounding interest, meaning at every moment of time it's compounding. This would never happen in a real life like banking scenario because you can't compound money continuously. This would, however, happen for something like radioactive decay or a population growth because that is continuously doing something. But we can use it as an idea to look into these things for money. This is actually would be an upper bound. You can't gain any more interest than the continuously compounding one. It's the most you can get. Okay. A is the amount earned after a certain period of time. P is the initial investment called principal, and this is going to be the $25,000. And the 5 years is the T. T is always in years, so it's going to be 5 years. R is the interest rate, which is at 5%, but you write this as a decimal, so 0.05. And then N, which you can see here, we have N for this first part. N is not involved here because it is continuously compounding. N is how often it is compounded per year, per unit of T, so per year. Like I said, the second function doesn't have it because it's continuously compounding. And we have different values. So for A, for N, we have A, maybe like this. N equals, it says A is compounded semi-annually, in other words, twice a year, 2 times per year. For B, N is compounded quarterly, so 4 times per year. For C, compounded monthly, so N is 12 times per year. And then D is compounding continuously, so we're going to use the other function for that. So for the first 3, we're going to use this function. The second, the last one, we're going to use this last function. And all I'm doing here is I'm just going to plug this into the formula. So I'll show you for part A. A is A equal to P1 plus R over N to the NT. We're trying to figure out what is A when P is 25,000. 1 plus 0.05. And then for part A, it says compounded semi-annually. In other words, 2 times per year. So N is 2. And then to the NT, N is 2, NT is 5. So all I'm doing is I'm plugging this into a calculator and solving. And doing that, for the first one, I get $32,000. $2. I'm going to round to the nearest cent, so $32,002.11. And that's from the starting amount of $25,000. So we gained about $7,000 by doing that. 32002.11. Okay, the next one, the only thing that's being changed here is N equals 4, compounded quarterly. So N is going to equal 4. So I'm going to have, I can just actually copy this thing. Copy it and then paste it. Equals the same thing, but all I'm changing is N equal to 4. And then for the last one, so this is part A, this is part B. For the last one, part C, I'm again taking the whole thing and all I'm changing is N I shouldn't say last part, I should say the third part. The last part's the continuously compounding one. And it's per month, so it's going to be 12. And part D I will talk about in just a moment. So let me get these numbers for you. Okay, so for part A, we found that compounding twice a year is $32,002.11. Then compounding 4 times per year, we got more money actually, $32,000, $50.93. And then for compounding monthly, we have $32,083.97. So the more times you compound, the more money you make in general. Now, this of course aren't that much different. I mean, 50 and 80 is not that, it is a pretty big difference. But compared to the fact that it's $32,000, it's not that big of a difference. However, if you were to consider this thing over a long period of time, say 30 years, there'd be a much bigger difference between these numbers, and it would be much more significant to you. Okay, so getting these typed in, those are what I have for those 3 parts. Part D is slightly different. We're using this formula, APERT as it's called for short. The parts are still the same. We have the amount is going to be the principal, the starting amount, times, and now we have E, the Euler's number E, to the power of the rate times the time, or the time in years is 5. It's 5 years. So that's all we have to do. So I'm just going to plug this into the calculator, and using E, that's E is the key here. Why we don't need N. There's good reasons for that. I'm not going to talk about that here, but you can use that to find this, and that gives us 32,164 cents. And this should always be the most that you find. As you can see, we kept getting more and more money, and this should be the highest number there. So that's what you'd expect. 0.64. Let's look at it. And that's all correct. So that's how you can use those formulas when you're calculating interest. Okay, write the following equation in its equivalent exponential form. This is very easy to do. All we're trying to do is change it from a logarithm to an exponent. Logarithms and exponents are inverses of each other, meaning you can change it from one form to the other very easily. In this case, we have log base 4, and that's the key. Whatever the base is, you're going to take that base to the power of both sides. So it's going to be 4 to the power of log base 4 of 64 and 4 to the power of y. So on the first side, the base 4 and the log base 4 cancel. They're inverses, so they will always cancel. And we're left with the 64 by itself. On the right-hand side, we have 4 to the power of y. And this is the exponential form. There's no logarithm here. It's just an exponent, 4 to the power of y equals, some number with some equation there. So 64 equals 4 to the power of y. And that's correct. Same idea, except now instead of going from logarithm to exponent, we're going from exponential to logarithmic. So we have 1 over 125 equals 5 to the negative 3. This is our exponent here, 5 to the power of negative 3. The base is 5, and that's the key. That's the key thing to note here. Base is 5. So what I'm going to do is I'm going to space this out just a little bit, because now I'm going to take log base 5 of both sides. Just like in the previous problem, we took 4 to the power of both sides. That's what canceled with the logarithm. Here we're going to take log base 5. 5 is the base. That's how we cancel. Log base 5 and the 5 will cancel, giving me just negative 3 on the right-hand side. And on the left-hand side, we have log base 5 of 125. and that is now logarithmic in form. So log base 5 of 1 over 125 equals -3. This font is very bad for this because a lot of students will think this is a capital I. It is a lowercase l for logarithm. So don't make that mistake. That's correct. Okay, you can calculate logarithms quite easily without the use of a calculator by making the inside have the same base as the logarithm. That's what we did here. We have log base 5 and 5 to the power of something. Those cancel. If we can do that here, then we don't need a calculator to solve this. So we have log base 16 of 4. You can't change the base, so leave the base as 16. What you're trying to do is figure out, how do I change 4? 4 is going to equal 16 to what power? To what power x? That's what we're trying to find here. And if you think about it, well, 4 is the square root of 16. Well, the square root of 16, so if we said it this way, 4 equals the square root of 16. The square root is the same thing as the power of 1/2. That's the same thing. They're both the same. So I can rewrite 4 as 16 to the 1/2. So let me write like this. Log base 16 of 4 is the same thing as log base 16 of 16 to the 1/2, right? 16 to the 1/2 is the same thing as 4. And now you see I have log base 16 of 16. They cancel, and that gives me 1/2. So I get 1/2 right there. Correct? We're trying to graph these two things on the plane, and the main thing you should note is that we have an exponential function here, and we have a logarithm with the exact same base as the exponential. That means these two functions are inverses of each other, so they should be reflected across the y equal to x line. So this diagonal line here, they should be reflected across that. And we showed in a previous problem that the 1/8 x, that looks something similar to this. It's not exact, but it's got the exact same shape. And reflecting that across the y equal to x line, I should do this in red really, this red line here, it's going to look something like this. Let's see if I can get it here. That's what we expect. And the closest one that looks to that is A. Definitely not B. B has a really weird reflection. I think it's reflecting across like a diagonal line that goes the other way. It's not C. C, it doesn't go down there at all. And definitely not D. So A is what we're looking for. Yep, that's correct. Okay, we're just going to graph the natural log of x and then graph the transformation. Yep, and then give the domain and range. All right, so we're going to start by graphing natural log of x. So let's do that here real quick. The natural log looks like this as a general function. So this is like natural log of x. In fact, log base anything looks a lot similar to this. This key point is at x equal to 1. Just like the exponential function had a key point at y equal to 1. This has a key point there. And that's what we're going to begin by looking at. So we're going to just do that here. You can see we have, this is a logarithmic, this is exponential. We have a logarithmic base e. Natural log is base e. This is the same thing as base e. And so that's the same function that I just drew here. That's the basic natural log function. Okay. Now we're going to transform it. 1 minus natural log of x. So if we had y equal to a f of x bx minus c plus d, Here we have something, it's slightly flipped. I can just do d plus a f of bx plus minus c. And that will show you that this 1 is just a positive 1 for d, right? We have 1 here. And then we have negative f of x. F of x is just the natural log of x, so we have 1 minus natural log of x. The function is the natural log. And so all we're doing here is showing that b is 1, c is 0, so those don't do anything. But d is positive 1, and a is a negative 1. So d is going to be a vertical shift upward. We know that one. Shift 1 unit upward. Oops. And the negative a means it flips it. And because it's on the outside, it's going to flip it vertically. Just like d flips it vertically, a is going to flip it vertically. So it's a flip or a reflection vertically. So if it goes from up here down to here and vice versa, and that flips it across the x-axis. That's a horizontal flip, so it's actually going to be part I here as well. A reflection across the y-axis is if b was negative 1. It's on the inside of the function, and that would flip it, if it's on this side, it's going to go over here and vice versa. That's across the y-axis. So it's not a horizontal shift, or a flip, I should say. It's a vertical flip, or a reflection. Okay, now we can graph it. We have a vertical shift of 1 unit, and we have a reflection over the x-axis. And that's what this looks like. We're going to shift it up 1 unit, so it's going to look like this, and then reflect it across the y-axis. It gets reflected across there. It's going to look like that, like this right here. So that's what we have. We want the asymptote as well, so I forgot to do that. There's a vertical asymptote. That's just right here at the y equal to x. Y equal to 0, no, x equal to 0 line. That's the vertical axis there. Vertical asymptote. X equal to 0. That's the equation of the vertical asymptote. That's it's the y-axis really. It's the same thing as that, so that's what that is. And the domain is going to be, well, the smallest value is getting close to 0, but not including 0, because it asymptotes to 0. And it does go off to positive infinity on the x-axis. So 0 to positive infinity, that's the domain. And the range, you can definitely see all positive values. And this does go down to negative infinity. It just takes a long time to get there on the range. So this is going to be from negative infinity to positive infinity. All right, let's see it. Okay, let me figure out what I missed here. Okay, I found my error. When I did this thing here, I put the vertical shift in first and then I reflected it. If you do that, what you end up doing, let me just delete this real quick. So if I do the vertical shift first, vertical shift upward, and then reflect over the x-axis, you see that the vertical shift becomes a negative 1. That's because when you do the vertical shift first, you increase 1, and then you flip over the x-axis. That gives you a negative 1. But that's not what you want. You want to have a reflection over the x-axis and then a vertical shift. And this will be correct. If you plug in the... No, that's not correct. There we go. That did it correctly. What you can always do is you can test points to make sure what you're doing is correct. But even better would be to just use another graphing software. These transformations can be finicky to knowing which one to do first and which one to do last. I don't ever remember which ones, what's the hierarchy for doing it. I just use a graphing software. So really just use that to help you graph it. The most important thing to be able to do is be able to read off What is the asymptote? What's the domain? What's the range? That's really the key thing to know here. If you test that, it's correct. Okay, moving on, we have write the equation in equivalent exponential form. It's logarithmic, so we're going to write an exponential, and then we're going to solve it. So the first step is to take the log base 3 and get rid of that. And we do that by taking the base 3 of both sides in a power. So it's going to be 3 to the power of this and 3 to the power of 2. That cancels this and leaves us with just the inside, so x minus 5. And then we have 3 to the power of 2 on the right-hand side. So this is now equivalent exponential form. That's the first part. Equals 3 to the power of 2. Okay, the next part is to solve for x. That's quite simple. X minus 5 is 3 squared is 9. So all we have to do is add 5. X equals 14. X equals 14. There are some things you have to concern yourself with, and that's to make sure that the inside of the logarithm, x minus 5, can never be negative or zero. That gives you an error. Those are not allowed in the domain of the function for the logarithm. So as long as you make sure x 14 minus 5 is 9, that's a positive 9, that is inside the domain, so that's good to go. That's going to be key for coming up videos or coming up sections. Okay, the last problem is a decibel loudness of sound. It's given by this function here. 0 is barely audible, and 160 will result a ruptured eardrum. If a certain animal it makes a sound that reaches intensity, I is the intensity here, of 4.6 times 10 to the 7 watts per meter squared. That's the unit for the intensity of sound. What's the decibel level? All we have to do, just plug it in and calculate. So log base 10 to the 12 times 4.6 times 10 to the 7. And I want to simplify. LOG by itself is the same thing as log base 10, but we don't write the base 10 because it's so commonly used that we just don't write it. I can combine these two things as 4.6 times 10 to the 19. And plugging it into a calculator. Let's see, 10 times log base 10, 4.6 times 10 to the power of 196.63. Rounds the nearest whole number, that'd be 197. And 160 will result in a ruptured eardrum. This is 197, so yes, that is a tremendously loud sound, and that's correct.